Welcome to the Foundry by Forge College. In today's explainer, we are capping off our Bitcoin fundamentals track, specifically diving into the advancements in Bitcoin, SegWit, and Taproot module. We're going to take what we learned in our last lesson about MAST and script flexibility and synthesize it to reveal what is literally the ultimate privacy glow-up in the entire Bitcoin protocol. I'm talking about Taproot. We're essentially moving from the blockchain equivalent of leaving your diary wide open on the kitchen table to an era of elegant cryptographic discretion. It's a massive shift, and it's incredibly cool.
So let's look at the blueprint index for today. We've got 6 parts to cover. First, the privacy blueprint. Then, a concept I call the house with hidden rooms. Third, we'll look at tweaked keys under the hood. Fourth, the efficiency boost. Fifth, Taproot's hidden trade-offs. And finally, number 6, the network effect.
All right, kicking things off with part 1, the privacy blueprint, recapping MAST and Schnorr.
Now, you might remember MAST from our last lesson, right? It's that feature that lets you carry a massive, messy, jingling ring of keys in your pocket, but you only ever have to show the one specific key you actually need to unlock a door. Well, Taproot takes that exact script hiding trick and pairs it with Schnorr-based key tweaks. When you add those two together, you get what we call Taproot indistinguishability. So what does this actually mean in plain English? It means that to anyone looking from the outside, a massive corporate multi-signature vault, a highly complex time-locked smart contract, and you simply buying a cup of coffee, they all look absolutely mathematically identical on-chain. There's literally no way to tell your multi-million-dollar vault apart from a quick caffeine run. How crazy is that? Moving right along to Section 2, Hidden Rooms, the Master Metaphor. To make this abstract cryptography a bit easier to visualize, let's use a structural metaphor. Imagine a large house. Pre-Taproot setups like your legacy multisig were essentially glass houses. They basically left your basement blueprints, all your specific spending rules, and your multiple signatures sitting right out there on the front lawn for any nosy neighbor to inspect. Not great, right? But Taproot is a solid brick house. It's got a perfectly normal-looking single front door, a master key, and a whole bunch of elaborate hidden basement rooms underneath the floorboards. It completely disguises your complex multisig contracts as a boring, standard single-door transaction.
Now, I want to draw your attention to this definition of that front door. Technically, we call this the tweaked key. Under the hood, this is an internal public key that's been mathematically modified by a commitment to an optional script tree. I know, that sounds super technical. But practically speaking, it is the ultimate disguise. You see, as long as everyone inside the house agrees to walk out that front door together, absolutely nobody on the outside will ever know about those crazy trapdoors you built down in the basement. It's brilliant.
Okay, Section 3, Tweaked Keys under the hood, looking at key path versus script path.
Let's break down how this actually builds mechanically when you go to authorize a transaction. It really all comes down to the order of operations between two things, a key path spend and a script path spend. Here's how it works. Step 1, you always default to a key path spend. That means using the master key on that front door we just talked about. Doing this leaves 0 footprint. It just looks like a clean, normal signature. Step 2 only happens if things go completely sideways. Let's say a business partner loses their key and you suddenly need to trigger a backup time lock. In that case, you use a script path spend. You're basically opening the hidden trapdoor from the basement. Now doing this does leak the Merkle authentication path to prove that that specific rule existed. So the golden rule here? Always try to take the front door.
On to Section 4, the efficiency boost and getting smaller footprints.
So this single door trick doesn't just grant you incredible privacy, it actually acts as a massive architectural efficiency boost. You see, doing things privately in this system actually means doing things smaller and lighter. Because Schnorr signatures are mathematically linear, multiple parties can actually mash their signatures together completely off-chain. Just picture 5 business partners combining their individual signatures into one perfectly normal-looking scribble before broadcasting it to the network. This completely eliminates all that old redeem script clutter, dramatically reduces the actual bytes you consume, and directly lowers your block-level fee cost. So you're getting better privacy and a cheaper bill. A real win-win.
Let's check out Section 5, Hidden Trade-offs, essentially the inspector's report.
Now look, no house is perfect, right? So let's put on our hard hats for a second and look at the real-world friction, the actual cost of this upgrade. As you dive deeper into other Forge College courses, you'll see developers face some real hurdles here. First off, we have key path dependence. Your privacy really only exists if you stick to that key path. If you're forced to use the script path trapdoor, well, you expose your intent. Second is tooling complexity. Wallets don't just magically aggregate all this stuff for you. It requires really complex multi-round coordination off-chain using protocols like multisig. And third, adoption friction. In a transitional network, having mixed transaction types floating around the mempool creates unpredictable fee dynamics while everyone else is slowly trying to catch up to the upgrade. It's a process, for sure.
Almost at the end. Section 6, the network effect, principles for synthesis.
Let's go ahead and distill all of this mechanical theory into 3 core principles you'll definitely want for your synthesis notes. Number 1, privacy depends entirely on your spending behavior. The key path front door absolutely must be your default. Number 2, efficiency requires complementary off-chain protocols. Taproot gives you the ability to save, but developers actually have to build the complex wallet tooling to realize those savings. And number 3, script path spending is certainly better than the old glasshouse, but it is not completely invisible. If you use it, it still reveals your intent for that specific branch you execute, even if the unused branches stay hidden.
Which brings us to a massive final thought for the broader ecosystem. If you can no longer tell a massive corporate multisig vault from a single user just buying a coffee, how will an entire neighborhood of these completely identical doors change block capacity, fee distribution, and the network mempools as a whole? It's a huge question, and it perfectly sets us up for our next explainer. Until then, review your notes, continue building your knowledge, and please head over to forge.college to explore more Web3 concepts. Catch you next time.